All right, students, we are back. Yes, let's do this. I just realized I kind of need more light in here. Hold a second for a moment. Yeah, that really helped. Anyway, uh, okay, welcome back. So let's see what we're going to be doing here right now. Uh, okay, go back here to our Canvas page. And this is the activity that we're doing. It's an assignment that is due by tonight at midnight. But again, if you're having any problems, just turn it in a little later. I'll keep track of things. Just don't wait until Sunday or something like that. Okay? I don't want you guys to get yourselves kind of like overloaded with stuff to catch up with. All right. So essentially, what we're going to do here is we are going to tackle two different kinds of problems. So I'm going to first deal with the first two, and then we'll talk about the other ones. Realize that for one of the activities, you will have to do a graph. Let me pull this down here for a moment so we can see the actual handout. So notice here for this last part, you are going to have to do a plot of pH versus milliliters. This is basically a titration experiment like the ones we discussed last time, where you follow the titration not with an indicator, but by tracking the pH. All right. So that is what we're going to be doing. And let me come back out here. So let's look at the assignment itself. Here we go. So here is the, oops, sorry. Bring us back over here, pin video. Oh, there we go. So here's the assignment. So how about if we, I'm going to walk you through these first two questions here. Uh-oh, we're getting blurry here. What happened? Okay. In the exercises that we did in our regular lecture time, typically we were given the components of the buffer. So the weak acid and its conjugate base, right? And we were asked questions about, the relative ratios, what would be the pH of it, things like that. But in these two questions, questions 1 and 2, what's going to happen is you only have one of the components, and then you have some other chemical to play with. So let's start out with the first one here, okay? It says you need to make a buffer that is pH 9.50 using an ammonia system. However, you only have a 0.400 molar solution of ammonium chloride and 1 molar NaOH. How would you prepare 50 milliliters of this buffer? So for your case, for your situation, guys, you are going to be doing this on a piece of paper. Okay, just handwrite it. Now, if you want to write it on a document and kind of type it and stuff like that, that's fine also. I personally am not good at handling formulas in word processing documents. So it's hard for me to make those, and I get all obsessive about it, and I try to, make it perfect, and I just end up wasting like a lot of time. So just do it on a piece of paper, and you can then, either take a picture and upload it or scan it to a PDF like we've talked about before. So whatever works for you, okay? Just I don't want to make it an issue as to how you submit the work, but that you, do it and you learn how to do it. All right. So let me get out of here and let's go ahead and do this. So, okay, so we are making a buffer. You know what? Let me make this a little more manageable here. Let me get this guy out of here. I don't think we need this back row here anymore. All right, so we're gonna make a buffer with just with ammonia and ammonium, but it turns out that we only have the one of the components. We only have the ammonium ion. All right, that's the whole thing here. Okay, where's my marker? So what I would say is the first thing you want to do is you want to set up what are the components of the buffer system. All right, that's the first thing you want to do. What are the components of the buffer system? All right, and in this case, we are talking about ammonium ions, and H plus and ammonia. Please get in the habit of writing things always in the direction of the acid ionization into its conjugate base. I know that with ammonia, we typically write it the other way around, what happens to the ammonia itself. But for purposes of a buffer, so we can use the Henderson-Hasselbalch equation, it's preferred to do it this way, all right? So let's apply the Henderson-Hasselbalch equation. I'm going to say that pH equals pKa plus the log of base over acid, which in this case would be ammonia, would be the conjugate base, and ammonium ions would be the acid here. Well, we have a problem here. What we have as far as information is concerned is the Kb of ammonia, not the Ka of the ammonium ion. So let's go ahead and calculate what that is. So Ka would be Kw over the Kb. Of course, Kw 10 to the minus 14. It's constant, right? You don't have to memorize it technically, but you should by now have used it enough that you remember what it is. And we were told that the Kb is 1.7 times 10 to the negative 5. So I'm going to skip the calculator here. I did find my calculator, but I'm not going to use it right now. So this would be 5.9 times 10 to the negative 10. So that means that the pK minus the log of that it ends up being 9.23. Don't forget, whatever number of sig figs you have in there, that's however many decimals you have in the logarithm. All right, so let's go back to Henderson-Hasselbalch. Our pH target is 9.50, and that would be 9.23 times the log of base over acid. So I'm going to skip a couple steps here. This means that I had to subtract this over here, and then I had to take 10 to that number to get the ratio. So what I'm trying to find here is, what is the ratio that I need of ammonia to ammonium ions? That's what I'm looking for. And that's going to be essentially 10 to the 0.27. That's the difference between 9.50 and 9.23. And that is 1.86. So essentially, I need a buffer where the ratio of ammonia to ammonium is 1.86. That makes sense, right? Because since the pH is a little higher than the pK, you expect for there to be a little more base than acid. So that makes sense. Always make sure before you commit yourself to these calculations, make sure that they make sense chemistry-wise, okay? So here's the problem. We don't have NH3. NH3 is not available. So what we're going to have to do is we are going to have to make it. You're going to make it. How do I make NH3? Well, the source of it has to be ammonium ions. But how do I get them to convert? Well, what I have to do is I have to neutralize some of the ammonium. So make it by reacting NH4 with NaOH. Acid, base gives me, right, the conjugates, which would be the ammonia. and the water. Cool. So let's set up our experiment. So what I'm going to do is I'm going to have NH4Cl, and I'm going to add NaOH. Now remember, this is a straight up reaction, okay? No equilibrium here. This is an acid-base reaction, and I get NH3 and NaCl and water. Everybody with me? Now, I'm going to go ahead and consider the following, all right? How many moles? How many moles of NaOH do I add? Now remember, in the end, this solution is going to be 50.0 milliliters. So the volume is going to be the same. Therefore, I can simply set up my equilibrium or my reaction with moles. So what I'm going to do is I'm going to do my little table, but this is going to be in moles, not in molarities. And the point is, I'm trying to find out for every mole of NH4Cl, how many moles of sodium hydroxide do I need? Right? So that when they react, I'm sorry. You generate the amount of ammonia you want. This is what we're looking for. I'm trying to find out, I want to find out how many moles of NaOH do I need to add in order to convert that amount of ammonium ions into ammonia. So this is not going to be equilibrium. This will be more like the end of it. You're going to have 1 minus X here. All of the hydroxide ions that I added are going to be consumed. I'm going to have X of ammonia, X of NaCl. And of course, I don't care about the water because that's a solvent. Okay, let me stop for a moment and make sure that we understand what we're doing here. Right? Remember, I don't have ammonia. I have to generate it. The only source of ammonia is if I can convert some of the ammonium ions into ammonia. The only way I can do that is by reacting the ammonium ions with sodium hydroxide. But I need to figure out how much. In other words, if I need to generate X moles of ammonia, that's going to come from the reaction of X moles of NaOH, right? So that's what I'm going to subtract from NH4Cl. Now, how do I find X? Well, remember, I need for the ratio of ammonia to ammonium to be 1.86. That has to be my ratio. Again, remember, we calculate by molarities, but remember, they're both going to be in the same volume. So I can simply go with moles here. And this is going to be ammonia, which is X. And ammonia will be 1 minus X. Okay. Remember, final volume is the same. So it's okay to do it with moles. All right. So you solve this equation here. That's a simple algebra equation there. And we find that X equals 0.650. I'm going to go with, I don't know, I'm going to go with 3/6 here. Everything that is showing me here has about 3 decimals of molarities anyway. So this is the moles of NaOH that I need for every mole of ammonium chloride in order to generate the proper ratio of ammonia to ammonium. But remember, in this problem, we're not adding solids, right? It's not like we started with ammonium chloride solid. We have a solution already. So what we're going to have to do here is we're going to have to figure out how does this work. All right. So let's say that V is the milliliters of NaOH that I'm going to add. And since the final volume is 50, that means that 50 minus V would be the milliliters of NH4Cl solution. All right. Because remember, although this tells me the number of moles, I need to figure out, okay, how do I get that many moles of NaOH into a solution that's going to end up at 50.0 milliliters, right? All right, so we said the moles of NaOH per mole of NH4Cl equals 0.650. All right. Okay, what are the moles of NaOH? Well, it would be the molarity of the NaOH, which is 1.00 molar. So that was 1.000 moles of NaOH in a liter, but let's say, 1,000 milliliters. Let me zoom in a little bit here. Right? And I need V milliliters of this guy, right? That's what I'm adding. And then for the ammonium chloride, I have 0.400 moles, that guy, in 1,000 milliliters, times milliliters will be 50 minus V. Why am I doing this? Well, remember, this is the moles to moles ratio. So these are the moles of NaOH, and these are the moles of NH4Cl. And sadly, I ran out of space here, so I'm going to have to switch this around. Let me give you a few seconds to check that out. Okay, I want to make sure you understand what we're doing here, right? Again, we needed to generate ammonia. To generate ammonia, we had to react sufficient moles of ammonium to get us the proper ratio here. But since we are adding liquids here, we had to figure out, well, how many milliliters of each? Well, since the ratio we have is in moles, we have to figure out, well, how do I get, so many moles of this guy with a solution that's 1 molar? How do I get these many moles of NH4Cl with a solution that's 0.4 molar? And making sure the ratio of volumes stays. So let me flip this around. Actually, I don't have a place in there for it. Oops, sorry, I turn it all around. Okay, so let me write that again that we just did, right? We said that the 1 mole of NaOH for every 1,000 milliliters, and we're going to add some number of milliliters of that to give us the proper moles of NaOH, right? And then we had 0.400 moles of ammonium chloride in a liter, or 1,000 milliliters. And we're going to add a complementary amount of liquid. The final volume has to be 50, so this is going to be 50 minus that. And this is, since this is going to end up giving me moles to moles ratio, this should be 0.650 here. So now I gotta solve, so I gotta move this over there, then I gotta move this over there, clear it out. So I'm gonna skip all these steps. I'm gonna skip the algebra and let you know that the volume here is 10.3. So we solve for V. So to make the solution, okay, to make 50.0 mLs of buffer, you add 10.3 milliliters of your 1 molar NaOH to 50 minus 10.3, which is 39.7 milliliters of your 0.4 molar NH4Cl. All right. And there's your answer. What's the moral of the story? Go to the stockroom and get yourself some ammonia and just do the buffer with ammonia and ammonium chloride. This is a lot of work to get this done. But like I said, the issue here is to see if we can, you know, kind of like play with these numbers and values and what buffers are to generate a buffer where you're missing one of the components. Okay. Okay. So let's see. Let me put you guys back in there just in case you need to see it again. That ending there. All right. So like I said, don't forget these things get scanned and they'll be part of your recorded lecture time. Whew. Questions? I realize you might be catching up, so I can wait a few more, about a minute or so. We're going to do another one now, similar to this one. Similar in the sense of strategies, right? All right. Okay, let me set this up for the next one. All right, let's see what the next question was. Okay, so the next question was, you need to, can get this guy to settle in there. Okay, you need to make a buffer that is pH 5.00 using the acetic acid acetate system. However, you only have solid sodium acetate trihydrate and 75 milliliters of 0.1 molar HCl. How would you prepare this buffer? So similar as before, you have to make a buffer, but you only have one of the components of the buffer. And then you have, in this case, a strong acid to deal with. All right. So as you can imagine, we're going to do a similar approach to what we did in the previous exercise, right? So let's get ourselves ready here. All right, let me bring in another piece of paper here. Let me see if I can write a little smaller this time so we don't run out of space and I have to go on the back of this sheet. Okay, the first thing I'm going to do is acetic acid has a, formula with several carbons, hydrogens, oxygens. Many times in these kinds of problems, we use abbreviations rather than the formula, all right? So I think I'm going to do that, all right? I'm going to just do that. So let's go ahead and do that. I'm going to call acetic acid, I'm going to call it HAC, and acetate, I'm going to call it AC minus. So acetic acid acetate. because the formulas here they're not really that super important in this case. Again, remember, whenever you're making a buffer, you want to write out what is the equilibrium in the direction of the ionization of the acid. So the acid is HAC, and it's ionizing into, again, H plus and acetate ions. And once more, the pH equals pKa plus the log of base, which is in this case the acetate, over the HAC. They give us the Ka of acetic acid, correct? It's in their problem here. It's 1.8 times 10 to the negative 5. So that means that the pK is minus the log of 1.8 times 10 to the minus 5. Oops, sorry. Our target pH is 5, so let's put in there 5.00. Minus the log of this is 4.74, plus the logarithm of acetate over acetic acid. We're going to do the same thing we did before. We're going to try to find out what is the ratio that I'm looking for here, right? So what would be the ratio of acetate base to acetic acid? And that would be 10 to the difference between these two, which is 0.26, right? Which is 1.82. Does that make sense? Well, yeah, because the pH is slightly more basic than the pK. That means that you have to add something here, and that means that this has to be a positive value, which means that that ratio has to be bigger than 1, and it is 1.82. All right? But again, like what happened before, is we have acetate, but we don't have acetic acid. So unlike the the virtual lab that you did on Tuesday, where you made, quote unquote, a buffer of acetic acid and acetate, in this case, you don't have the acetic acid. So we're going to have to make it. And the way to make it is we had to make it from our sodium acetate that we have already, right? Remember, we have some sodium acetate. Now, the sodium acetate we have is actually a solid. What we really have is a solution of HCl. So what we need to do is take that HCl and add some acetate to have a reaction where you end up with acetic acid and, of course, chloride ions. So that is our strategy. Now, I have a limited amount of this. I have 75 milliliters, and I forget what the precision level of this was. Let's see, 75.00, okay? 75.0 milliliters of a solution that was, 0.1. How many zeros do they have in there? Sorry, guys, I forget. 0.1. Wow, that's very precise. They're very well standardized. 0.1000 moles in 1 liter, in other words, in 1,000 milliliters. So that means that I have, this is divided by 10 and then divided by 1,000. 0.00750 moles of HCl. All right. That's what I have available to me in that sample of 75 milliliters. All right. So let's go ahead and set this up. Again, we're going to do again our HCl plus acetate. I want to generate acetic acid and chloride ions. All right. So let's start out again like before. We're going to tackle moles in here. We said we have 0.00750 moles of HCl. And I don't know, I need a certain number of moles of acetate to react with it. So when they react, we're hoping that, you know, some of that acetate reacts. Actually, I have this wrong here. Sorry. The idea here is that all of the HCl here is going to react, right? Right. Because I don't want any HCl left over at the end. This one also, let me put parentheses here so we don't get mixed up. All right, and of course this one also, but you know we don't care about the chloride ions here. They don't contribute anything to our buffer system. Okay, so at the end, we're gonna have 0 HCl left. We're gonna have X minus 0.007500. Guys, I'm running out of space here. Sorry, guys. These are kind of big numbers here. And we're going to end up with 0.00750 moles of acetic acid. Once more, at the end of it all of these moles of acid and base are going to be in a volume, 75 milliliters essentially. We're assuming that the amount of acetate we're going to add is not going to change the volume that much. All you're doing basically is you are essentially neutralizing all of the HCl in there to the point where you have enough leftover acetate and enough acetic acid to basically generate the ratio that you want. So the ratio that we want of acetate to acetic acid is 1.82. So that would be X minus 0.00750 divided by 0.00750. So this one's a little easier to solve than the one we had in the previous exercise, right? So what we get from here is multiply this out at 0.7500, and this ends up being 0.0212 moles. So in other words, the strategy is I had to add 0.0212 moles of acetate so that I can convert all of my HCl into acetic acid while leaving enough of a residue of acetate to generate that ratio in my buffer. All right, oops, sorry, let me pull this over here. So that means that I need 0.0212 moles. And they were kind enough to give us the, without the formula, they gave us the molar mass here, 136.08. Notice that this is a trihydrate. In other words, this is a hydrate compound. It's not anhydrous. It has 3 molecules of water for every unit of the sodium acetate. So this is 136.08 36.08 grams in 1 mole, which comes up to be roughly about 2.88 grams of sodium acetate, trihydrate. All right, so you're gonna take your 75.00 mLs of HCl at 2.88 grams of sodium acetate trihydrate. And that's how you're gonna get your buffer in this case. Once more, the moral of the story is, just see if they have some acetic acid in the stock room, and you can do it the same way you did the exercise that we did on Tuesday, right? Anyway, there goes that. Cool. Let me know if there's any questions here.
Professor, can you raise the paper up a little bit?
How about if I just zoom out of there a little bit more? Oh, I guess not. I guess that's just there.
Yeah,
Sorry.
thank you.
One of these days, I'll get me one of those fancy iPads that I can connect to my computer and all that kind of stuff. Not there yet. Cool. All right, let me know if there's any questions so far here. All right. Well, let me do this. Let's gonna go ahead and take a quick break here.